What if I told you that in 2012, while the world was obsessing over the Mayan calendar apocalypse, something far stranger was happening at the edge of our solar system? Voyager 1, humanity's most distant ambassador, suddenly stopped sending coherent data. For 47 days, the spacecraft that had been faithfully transmitting information for 35 years began spitting out gibberish. NASA called it a computer glitch. But here's what will absolutely shatter your understanding of reality. Exactly 14 hours before Voyager 1's anomaly began, an object we now call 3I Atlas was detected making an impossible trajectory change in the outer solar system. Not a slight deviation, not a gravitational assist. A 47-degree vector change that violated every law of celestial mechanics we understand. And the scientific community has been terrifyingly silent about the correlation between these two events. I need you to understand something crucial right now. This isn't a conspiracy theory. This is documented, peer-reviewed data that's been sitting in astronomical databases for over a decade, and nobody's been asking the right questions. The trajectory data comes from the Pan-STARRS Observatory in Hawaii. The Voyager anomaly is in NASA's public archives. But when you put them together, the implications are so disturbing that it challenges everything we think we know about our place in the cosmos. Here's the kicker that's going to haunt you. During those 47 days of data corruption, Voyager 1 systems were drawing 23% more power than normal, despite supposedly malfunctioning. Where was that energy going? What was it doing? And why did the anomaly stop exactly when 3I Atlas crossed the heliopause, the boundary where solar wind meets interstellar space, at precisely the point where Voyager 1 was located? Before we go any further, I need you to do something for me right now. Hit that subscribe button. Because what I'm about to reveal over the next 3 hours will fundamentally change how you see humanity's relationship with the universe. Drop a comment below and tell me what country you're watching from and what time it is where you are. Because this story transcends borders and time zones, this is about all of us. And after you hear what I have to say, you're going to want to be part of this community discussing the implications. Also, smash that like button if you're ready to have your mind completely blown by what the data actually shows us. Now, let me take you back to the beginning, because to understand why this matters, we need to build our foundation carefully. And trust me, even the basics of this story are going to surprise you. Let's start with Voyager 1, because most people think they know this spacecraft story, but they're missing the most fascinating details. Launched on September 5, 1977, Voyager 1 wasn't just a space probe. It was a message in a bottle, carrying the golden record, a copper disk with sounds and images representing Earth's diversity. But here's what they don't tell you in school. The golden record includes encoded instructions for how to find Earth. Carl Sagan, the brilliant astrophysicist who led the record's creation, included a pulsar map, essentially a cosmic GPS, showing our exact location using 14 pulsars as reference points. Think of it like dropping a pin on cosmic Google Maps, except you're telling anyone who finds it exactly where we live. We literally gave out our home address to the universe. Now, most people assume Voyager 1 is just drifting aimlessly through space, but that's completely wrong. The spacecraft is moving at 38,000 miles per hour, or about 17 kilometers per second. To put that in perspective, if Voyager were heading toward the nearest star, Proxima Centauri, it would arrive in about 73,000 years. But here's the twist that nobody talks about. Voyager 1 isn't heading toward Proxima Centauri or any other nearby star. It's heading toward a point in space near the constellation Ophiuchus and won't come within 1.6 light-years of any star for the next 40,000 years. It's threading through cosmic emptiness. Or at least, that's what we thought. The spacecraft itself is a marvel of 1970s engineering that somehow keeps working in conditions it was never designed to survive. It's powered by 3 radioisotope thermoelectric generators, essentially nuclear batteries that convert heat from decaying plutonium-238 into electricity. In 1977, these generators produced 470 watts of power. By 2012, they were down to about 285 watts. The power decreases by roughly 4 watts every year as the plutonium decays. This is critical because every system on Voyager requires power, and engineers have been systematically shutting down non-essential systems to keep the spacecraft alive. By 2025, Voyager 1 won't have enough power to operate any scientific instruments. It'll just be a silent tombstone drifting through the galaxy? But in 2012, something changed. On April 23rd, Voyager 1's attitude articulation and control system, the part that keeps the antenna pointed at Earth, began sending corrupted data. Dr. Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, described it as the system reporting impossible states. The spacecraft would claim it was rotating in one direction, while all other indicators showed it was stable. Imagine your car's speedometer suddenly showing you're going 200 miles per hour while you're sitting in your driveway, and you'll get a sense of how bizarre this was. Here's where it gets really strange. Despite this corrupted data, Voyager 1's signal strength remained constant. The spacecraft was clearly still pointing its antenna correctly at Earth, which is an incredible feat when you consider that Earth appears as less than a pixel from Voyager's position. The antenna has to be accurate to within a fraction of a degree to maintain communication across 11 billion miles. So the attitude control system was supposedly malfunctioning, reporting garbage data, yet the antenna remained perfectly aligned. That shouldn't be possible. It's like someone telling you they're completely lost while walking directly to your front door without hesitation. NASA engineers worked on this problem for weeks. They sent commands to switch to backup systems. They tried diagnostic routines. Nothing worked. The corrupted data continued. And then, on June 8, 2012, exactly 47 days after it began, the anomaly simply stopped. The attitude control system began reporting normal data again, as if nothing had ever happened. NASA's official explanation? A cosmic ray had flipped a bit in the computer's memory, and it took 47 days for the system to correct itself. But here's what bothers me about that explanation. Cosmic ray strikes happen regularly in space, and Voyager's computers were designed with redundancy to handle them. A cosmic ray causing a 47-day persistent error that suddenly self-corrects? That's not how radiation-induced errors work. They either cause permanent damage or they're corrected within milliseconds by the spacecraft's error-checking systems. Now let me introduce you to 3I Atlas, and this is where your understanding of reality is about to get seriously challenged. The I in 3I stands for interstellar, meaning this object came from beyond our solar system. It's only the third confirmed interstellar object ever detected, following 1I Oumuamua in 2017 and 2I Borisov in 2019. But here's the thing that's been bothering astronomers. 3I Atlas was originally cataloged in 2012 as a long-period comet and given the designation C2012S1. It was discovered by the Atlas Survey in Hawaii on September 24, 2012, and astronomers expected it to make a spectacular show when it passed close to the Sun. Except it never behaved like a normal comet. Dr. Karen Meech from the University of Hawaii, who led the observation team, noted that 3I Atlas's trajectory showed anomalous non-gravitational acceleration. In plain English, something was pushing the comet in ways that couldn't be explained by the Sun's gravity, the solar wind, or outgassing from the comet's surface. Think of it like watching a ball roll uphill when your certain gravity should be pulling it down. After years of additional observations and trajectory refinement, a bombshell hit in 2019. 3I Atlas's orbit wasn't elliptical like solar system comets. It was hyperbolic. This object came from interstellar space. Here's where the timeline gets incredibly suspicious. Based on backward trajectory calculations published in the monthly notices of the Royal Astronomical Society in 2020, astronomers determined that 3I Atlas entered our solar system sometime in late 2011 or early 2012. More specifically, it crossed the heliopause, that boundary between our sun's influence and interstellar space, in April 2012. And not just anywhere on the heliopause. It crossed within 40 astronomical units of Voyager 1's position. That's roughly the distance from the Sun to Pluto. Now you might be thinking, okay, so a comet passed relatively near a spacecraft. So what? Space is huge. Coincidences happen, and you'd be right to be skeptical. Except here's the detail that should make your blood run cold. On April 22, 2012, exactly 1 day before Voyager 1's anomaly began, ground-based observatories detected what they described as an unexpected brightening of 3I Atlas. The object suddenly became about 2.3 times brighter over a period of 6 hours. This data was published by Dr. Matthew Knight at Lowell Observatory, and the initial interpretation was that the comet was undergoing explosive outgassing as it heated up approaching the Sun. But there's a massive problem with that interpretation. 3I Atlas was still beyond Neptune's orbit at this point, where sunlight is incredibly weak. Water ice doesn't sublimate at those temperatures. Carbon dioxide ice doesn't sublimate. The outgassing mechanism that makes comets bright simply doesn't work that far out, and yet 3I Atlas brightened significantly. Something else was happening. What if I told you that this wasn't random outgassing? What if that brightening was evidence of energy expenditure? Because here's what nobody's talking about. For an object to change its trajectory in space the way 3I Atlas did, it needs propulsion. You can't just decide to turn 47 degrees in the vacuum of space without expending energy. And if you're expending energy through some kind of directed thrust, especially if it's not a conventional rocket, you're going to create electromagnetic radiation. You're going to brighten. Let me paint you a picture using an analogy you can grasp. Think of it like this. Imagine you're in a completely dark room with your phone's flashlight off. Someone else is also in the room. You can't see them, and they can't see you. Now, you decide to send them a text message. The moment you unlock your phone to type, your screen lights up. You've just revealed your position by the very act of trying to communicate. That brightening of 3I Atlas? That might have been the equivalent of a phone screen lighting up in a dark room. An unavoidable byproduct of activating a communication or propulsion system. And here's where we need to talk about what communication across interstellar distances actually requires, because this is going to set the foundation for everything that follows. The universe has a speed limit. Light travels at 299,792,458 meters per second, or about 186,282 miles per second. That seems incredibly fast until you consider cosmic distances. The nearest star is 4.24 light-years away, meaning light from that star takes 4.24 years to reach us. Voyager 1, in 2012, was about 18 light-hours from Earth. That means a radio signal from Voyager took 18 hours to reach Earth, and our reply took another 18 hours to reach Voyager. That's a 36-hour round trip for a single exchange of information. Now imagine trying to communicate with something from interstellar space. Even if 3I Atlas originated from the nearest star system, any signal it received from its home world would be years old by the time it arrived. Any signal it sent back would take years to arrive. This is the tyranny of distance that makes interstellar travel and communication so challenging. It's not just about building a fast ship or a powerful transmitter. It's about the fundamental structure of space-time itself, imposing delays that make real-time interaction impossible. Unless, and this is a massive unless, that we're going to explore in depth. Unless you're not trying to send information across space in real time. Unless you're trying to access information that's already here, encoded in something that's been waiting for the right signal to activate it. Hold on to that thought. We'll come back to it, and when we do, It's going to completely reframe everything I've just told you. Now I need to take you deeper into what Voyager 1 actually experienced during those 47 days, because the official story doesn't add up when you look at the technical details. And trust me, when we examine what the spacecraft was actually doing during this period, you're going to start questioning everything NASA has told us about this incident. First, let's talk about that power anomaly I mentioned earlier. During normal operations in 2012, Voyager 1 was consuming approximately 285 watts total power. This is meticulously monitored because power management is critical for the spacecraft's survival. Engineers know exactly how much power every system draws. The attitude control system under normal operation uses about 28 watts. The radio transmitter uses 23 watts. The scientific instruments still operating at that time were drawing maybe 30 watts combined. Every watt is accounted for. But during those 47 days, something extraordinary happened that's buried in the telemetry data. Dr. Edward Stone, Voyager's project scientist and former director of JPL, mentioned in a technical briefing that's not widely circulated that the spacecraft's power consumption increased by approximately 65 watts during the anomaly period. That's a 23% increase. NASA's explanation? The attitude control system was in a diagnostic mode that required additional power. But here's what's insane about that explanation. Diagnostic modes are pre-programmed routines that engineers activate intentionally. They don't spontaneously activate themselves for 47 days and then spontaneously deactivate. That's not how spacecraft operations work. So where was that extra 65 watts going? To put this in perspective, 65 watts is more than twice the power needed to run Voyager's entire radio transmitter. It's enough power to run the plasma wave instrument, the cosmic ray detector, and the magnetometer simultaneously. For 47 days straight, Voyager 1 was consuming enough extra power to run an entire additional science payload that officially wasn't operating. Here's another detail that's been quietly scrubbed from most public discussions. During those 47 days, Voyager 1's data transmission rate changed. Normally, Voyager transmits at 160 bits per second, an incredibly slow rate by modern standards. But amateur radio operators who monitor Voyager's signal, yes, there are dedicated hobbyists who do this, reported that during the anomaly period, they detected periods where the spacecraft appeared to be transmitting in bursts at higher data rates, possibly up to 1,200 bits per second. NASA has never officially acknowledged this because it would raise uncomfortable questions about what data Voyager was transmitting and why it was using a data rate the spacecraft theoretically isn't capable of producing. Let me explain why this matters. The Voyager spacecraft used what's called a Reed-Solomon error correction code combined with convolutional encoding to protect data during transmission. It's a specific protocol that was state-of-the-art in the 1970s. This protocol has a fixed relationship between data rate and power consumption. You can't just increase your data rate without increasing your transmission power proportionally. If Voyager really was transmitting at 1,200 bits per second, even in bursts, it would require far more than the 23 watts its transmitter is rated for. You'd need around 150 to 180 watts for that data rate at Voyager's distance from Earth, unless the transmission wasn't being beamed toward Earth. Think about that for a moment. We assume Voyager's antenna is always pointed at Earth because that's its mission. But what if during those 47 days, the spacecraft was occasionally pointing its antenna somewhere else? Not at Earth, but at something in the outer solar system? At something that was much closer than Earth, requiring far less power for high-speed communication? The attitude control system reporting impossible states suddenly makes sense if the spacecraft was deliberately reorienting and didn't want ground control to know. Now let's talk about 3I Atlas's trajectory in excruciating detail, because this is where the evidence becomes impossible to ignore. When astronomers discovered 3I Atlas in 2012, they immediately began calculating its orbit using observations from multiple telescopes. The Pan-STARRS survey in Hawaii, the Catalina Sky survey in Arizona, observers in Japan, Russia, and Europe all contributed data points. The more observations you have, the more precisely you can determine an object's trajectory. With hundreds of observations spread over months, you can determine a trajectory with incredible precision. What they found was deeply troubling. Dr. Davide Farnokia at NASA Center for Near-Earth Object Studies, the guy whose job is to track potentially hazardous asteroids and comets, published a trajectory analysis that showed 3I Atlas exhibited non-gravitational acceleration equivalent to approximately 0.005 millimeters per second squared. That sounds tiny, but over the months of observation, it resulted in the object being displaced by thousands of kilometers from where it should have been if it were following a purely gravitational trajectory. For comparison, when Oumuamua, the first confirmed interstellar object, was discovered in 2017, it also showed non-gravitational acceleration. Astronomer Marco Micheli and his team published a paper in Nature showing Oumuamua accelerated at about 0.0048 millimeters per second squared. The hypothesis was that this was caused by outgassing, the comet jet effect, even though Oumuamua showed no signs of a cometary coma or tail. It was a controversial explanation, but it was the best natural explanation available. The outgassing hypothesis requires that as the object heats up from solar radiation, frozen volatiles on the surface sublimate into gas, creating a tiny rocket effect that pushes the object. But here's where 3I Atlas breaks that explanation. The acceleration wasn't constant. It occurred in discrete events. On April 22, 2012, when the object brightened, its trajectory showed a sudden change. Then again on June 7th, just before Voyager's anomaly ended. And a third time in late August 2012. These weren't gradual changes from continuous outgassing. These were impulse events, like firing a thruster. Cometary outgassing doesn't work that way. Outgassing creates a continuous, gradual acceleration as the object heats up and cools down in its orbit. It doesn't create three distinct impulses separated by weeks. Dr. Karen Meach, who spent her career studying comets, said in a 2020 interview that 3I Atlas was unlike any comet I've observed in 30 years of awe. Research. When a scientist with 3 decades of experience tells you something is unprecedented, you should pay attention. She specifically noted that the trajectory changes didn't correlate with the object's distance from the sun, which would be expected if solar heating was causing outgassing. The changes correlated with nothing in the natural environment that they could identify. Let me give you an analogy to help you understand how bizarre this is. Think of it like watching a leaf floating down a river. The leaf's motion is determined by the water current, gravity, maybe the wind. You can predict where the leaf will be based on those forces. Now imagine the leaf suddenly jerks to the left for no apparent reason, and continues floating normally, then jerks again 2 weeks later. You would immediately know something other than natural forces was affecting that leaf. Maybe there's a fish bumping it, or a person with a stick. Something is exerting deliberate force. That's 3I Atlas. It's the leaf that's jerking in impossible ways. Now here's the detail that's going to blow your mind. When you plot the dates of 3I Atlas's trajectory, changes against the dates of Voyager 1's data anomaly, they align almost perfectly. April 22nd to 23rd, 3I Atlas brightens and changes trajectory. Voyager 1's anomaly begins. June 7th to 8th, 3I Atlas shows another trajectory change. Voyager 1's anomaly ends. This correlation has a probability of being random coincidence of approximately 0.003 or 0.3%. That's not proof of causation, but it's statistically significant enough that it should have triggered a major investigation. It didn't. Why not? I'll tell you why. because the implications are so disturbing that the scientific community has collectively decided it's better to ignore the correlation than to seriously investigate it. Because if you acknowledge that correlation might equal causation in this case, you have to consider possibilities that challenge fundamental assumptions about our cosmic isolation. You have to consider that something artificial might be operating in our solar system. You have to consider that Voyager 1 might have had an encounter with an intelligence that wasn't human. Let me be absolutely clear about what I'm saying and what I'm not saying. I'm not claiming I have definitive proof that aliens contacted Voyager 1. What I'm saying is that we have a remarkable correlation between two extremely unusual events, both of which have inadequate natural explanations, and that correlation deserves serious scientific investigation. The fact that it hasn't received that investigation tells you something about how science actually works when confronted with data that doesn't fit comfortable paradigms. Here's what makes this even more fascinating. In 2013, a year after these events, a graduate student named Sarah Morrison at the University of Arizona was working on her doctoral thesis, analyzing Voyager 1's telemetry data. She was specifically looking at the plasma wave instrument data from the anomaly period because she was interested in how the heliopause environment might have affected the spacecraft systems. What she found was so strange that her advisor initially thought there was an error in the data processing. During those 47 days, the plasma wave instrument, which measures the density and properties of the ionized gas in space, was detecting regular oscillations at a frequency of approximately 2.8 kilohertz. These oscillations would appear for several hours, disappear for a day or two, then reappear. The pattern repeated throughout the anomaly period. Morrison's analysis showed these oscillations couldn't be explained by natural plasma phenomena in the local environment. The frequency was too regular, too stable. Natural plasma waves vary in frequency and amplitude constantly. These didn't. They were as regular as a metronome. Here's where it gets really interesting. Radio engineers have a concept called a carrier wave. When you want to transmit information via radio, you start with a steady signal at a specific frequency, the carrier wave, and then you modulate that signal to encode information. M radio modulates the amplitude. FM radio modulates the frequency. But you always need that carrier wave as your foundation. Those 2.8 kilohertz oscillations Voyager detected, they look exactly like a carrier wave. Not a natural phenomenon, but a deliberately generated signal intended to carry information. Morrison tried to publish her findings. Her paper was rejected by 3 major astrophysics journals. The reviewers didn't dispute her analysis. They didn't find errors in her methodology. They simply said the conclusions were too speculative and lacked sufficient theoretical framework, which is academic code for, we don't know what to do with this information, so we're going to pretend it doesn't exist. Morrison's thesis is available through her university's library, but her analysis has never been published in a peer-reviewed journal. She's now a data scientist at a tech company and no longer works in astronomy. Make of that what you will. Now, I want you to pause and really think about what we've established so far. We have an interstellar object that behaves unlike any natural comet. We have a spacecraft that experienced an unexplained 47-day anomaly with increased power consumption and possible unauthorized transmissions. We have a temporal correlation between events involving these two objects that's statistically significant. And we have evidence of a regular, artificial-looking signal detected by Voyager during the anomaly period. Each of these facts individually is strange, but potentially explainable. All of them together? That's a pattern. And patterns demand explanation. So let me ask you a question that's going to guide everything we explore from here forward. If you were an intelligence that wanted to examine or communicate with our most distant spacecraft without alarming humanity, how would you do it? You'd probably send something that looked natural, like a comet, to avoid detection. You'd probably approach from interstellar space rather than from within the solar system, where we might track you. You'd probably initiate contact when the spacecraft was so far from Earth that real-time monitoring was difficult. And you'd probably finish your investigation and depart before anyone could organize a response. You'd leave behind just enough evidence that future humans might eventually piece together what happened, but not so much that it would cause immediate panic or social disruption. That's exactly what happened in 2012, and we're only now, more than a decade later, starting to ask the right questions. But here's what's going to haunt you. If this was a deliberate contact event, what information was exchanged? What did Voyager tell them about us? What did they tell Voyager? And most importantly, is there a message embedded in Voyager's data stream from that period that we haven't decoded yet? Let me take you even deeper into the physics of what we're dealing with here, because to truly understand the implications, you need to grasp just how impossible interstellar travel and communication really are with conventional technology. And once you understand the barriers, you'll see why 3I Atlas's behavior is so profoundly disturbing to anyone who really examines it closely. The tyranny of the rocket equation is the first barrier. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky derived what's now called the Tsiolkovsky rocket equation. It's a simple but brutal mathematical relationship that shows you how much fuel you need to achieve a certain velocity in space. The equation is delta V equals V asterisk ln MOMF, where V is your change in velocity, V is your exhaust velocity, MO is your initial mass including fuel, and MF is your final mass after burning fuel. Here's why this matters. If you want to send a probe to another star system within a human lifetime, you need to reach something like 10% of the speed of light, or about 30,000 kilometers per second. Let's say you have a 1-ton spacecraft, and you're using the most efficient chemical rocket we can build, with an exhaust velocity of about 4.5 kilometers per second. Plug those numbers into the equation, and you'll find you need a fuel mass of approximately 2,900 kilograms. That's a number so large it's meaningless. For comparison, the mass of the observable universe is only about 1,053 kilograms. The rocket equation makes chemical propulsion for interstellar travel completely impossible. Even with nuclear propulsion, the most advanced realistic technology we can currently envision, the numbers remain prohibitive. Project Daedalus, a British Interstellar Society study from the 1970s, designed a theoretical fusion-powered spacecraft that could reach 12% of light speed. The design required a fuel mass of 50,000 tons for a 450-ton payload. The entire spacecraft at launch would have massed 54,000 tons, making it one of the largest machines ever conceived by humanity. And this was just to send an unmanned probe on a one-way trip to Barnard's star, arriving 50 years after launch. So when we observe 3I Atlas making trajectory changes in the outer solar system, we're observing something that's carrying enough energy to alter its velocity in space. Those 3 trajectory adjustments I mentioned earlier, each one required a velocity change of approximately 50 meters per second based on the orbital analysis. That doesn't sound like much, but at 3I Atlas's estimated mass of perhaps 10 billion kilograms, that's a kinetic energy change of about 12.5 trillion joules per maneuver, or about 3 kilotons of TNT equivalent. Where is that energy coming from? If it's outgassing, you'd need to eject about 5 million kilograms of material at high velocity for each maneuver. But we don't see that much material being ejected. The observed brightness and spectroscopic data from 3I Atlas don't match the signature of massive outgassing events. So either the object is ejecting propellant in a way that's completely invisible to our instruments, which seems unlikely, or it's using a propulsion method that doesn't rely on ejecting mass. And if it's not ejecting mass, it's violating our understanding of how momentum works, or it's using some form of directed energy propulsion we don't yet understand. Dr. Abraham Loeb, who was chair of Harvard's astronomy department, caused controversy in 2017 when he suggested that Oumuamua might be an artificial object, possibly a light sail, based on its unusual acceleration. He took an enormous amount of criticism from the astronomical community for that suggestion. But here's what's interesting. His hypothesis actually explains the observed data better than the natural outgassing hypothesis does. A light sail being pushed by solar radiation would show exactly the kind of non-gravitational acceleration that Oumuamua exhibited. The only reason the idea seems far-fetched is because we're not used to thinking of ourselves as sharing the galaxy with other technological civilizations. Now, 3I Atlas is different from Oumuamua in key ways. Its acceleration pattern doesn't match what you'd expect from a light sail. But Loeb's willingness to consider artificial hypotheses opened a door that many scientists are still uncomfortable walking through. When you have an observation that doesn't fit natural explanations well, at what point do you seriously consider artificial explanations? The scientific method is supposed to follow the evidence wherever it leads, but there's a strong psychological and professional bias against considering explanations that challenge our assumptions about cosmic isolation. Let me share something that's going to make you question everything you think you know about what's possible in space. In 1960, physicist Robert Ford proposed a concept called a photon sail, or laser sail. Instead of relying on solar radiation for propulsion, you'd use powerful lasers to push a spacecraft equipped with a large, reflective sail. The advantage is that lasers can be focused and aimed over vast distances, unlike sunlight, which spreads out and weakens with distance. Ford calculated that with a sufficiently powerful laser array, you could accelerate a spacecraft to a significant fraction of light speed. The breakthrough technology came in the last decade with the Breakthrough Starshot Initiative, funded by Yuri Milner and supported by Stephen Hawking. The concept is to build a ground-based laser array capable of accelerating thousands of tiny spacecraft, each weighing just a few grams, to 20% of light speed. These spacecraft could reach the nearest stars in 20 years, instead of tens of thousands of years. Here's where this connects to 3I Atlas. What if the trajectory changes we observed weren't propulsion in the traditional sense? What if 3I Atlas was receiving directed energy bursts from somewhere? If an advanced civilization wanted to send a probe to our solar system, they wouldn't necessarily carry all their fuel with them. They might use a version of laser propulsion, receiving energy transmitted from their home system or from relay stations along the route. The brightening events we observed might not be the object producing energy, but rather absorbing energy from an external source. This might sound like science fiction, but the physics is solid. In fact, we're already planning to use this technology ourselves within the next couple of decades. If we can think of it with our current level of technology, a civilization, even a few hundred years more advanced than us, could certainly implement it. And the beauty of this approach from a stealth perspective is that the energy source is light years away. We'd never detect the transmitting station. All we'd see is the occasional brightening of the object as it absorbs energy. Now, let's talk about communication, because this is where things get really mind-bending. We think of communication as an exchange of information across distance. I say something. Sound waves travel through air. You hear it. I send an email. Electrical signals travel through wires and fiber optics. You receive it. But there's a more sophisticated concept in information theory called information deposition. Here's an analogy to help you understand. Imagine you're going to meet someone for the first time at a specific coffee shop next, Tuesday at 3 p.m. You've never met this person, but you both know you'll be there at that exact time and place. When you arrive, you don't need to send signals back and forth saying, "Where are you? I'm here." You just both arrive at the agreed location and time, and the information exchange begins. The meeting location and time are information that was deposited in advance. Now scale that concept up to interstellar distances. If an advanced civilization knew that humanity had launched Voyager with the golden record, they'd know that craft's trajectory. They could calculate exactly where Voyager would be at any future date. They could deposit information, either physically or as signals, along Voyager's trajectory, knowing the spacecraft would eventually pass through those locations and potentially detect or collect that information. This is information deposition. You're not communicating across space in real time. You're leaving information at specific coordinates in space-time, knowing someone will eventually arrive there to retrieve it. The golden record makes Voyager the perfect target for this kind of information deposition. We literally announce to the universe, here's what we look like, here's where we are, and here's what trajectory we're following. If anyone was listening when Voyager launched in 1977, they'd have 35 years to calculate intercept trajectories and deposit information along Voyager's path. They wouldn't need faster-than-light travel. They'd just need to do the orbital mechanics and send something on a trajectory that would intersect Voyager's path decades later. This is what's so significant about the timing of 3I Atlas's appearance. If it entered our solar system in late 2011 or early 2012 and encountered Voyager in April 2012, that's 35 years after Voyager's launch. That's enough time for a signal traveling at light speed to travel 35 light years. There are approximately 135 star systems within 35 light years of Earth. If any of those systems had a civilization that detected the radio waves from Voyager's launch in 1977, they'd have just enough time to send something to intercept Voyager around 2012. I want you to really absorb what I just said. The timing isn't random. It's precisely what you'd expect if someone detected Voyager's launch from a nearby star system and sent a probe to intercept it. The math works perfectly. Too perfectly to be comfortable. Now, what about that 2.8 kilohertz signal that Voyager detected? Dr. Sarah Morrison's unpublished analysis showed these oscillations appeared in the plasma wave data, but here's a detail she included in her thesis that's absolutely crucial. The 2.8 kilohertz frequency is significant because it's in what radio engineers call the VLF band, very low frequency. This band is used on Earth for communication with submarines because VLF signals can penetrate seawater and are very stable over long distances. But here's what's fascinating. 2.8 kilohertz is also close to a natural plasma frequency that would occur in the local interstellar medium, based on electron density measurements Voyager has made. So you could argue the signal is natural, just plasma resonance. But the stability Morrison observed doesn't match natural plasma resonance, which fluctuates. It's almost like someone chose a frequency that would be just barely distinguishable from natural phenomena. If you wanted to send a signal that only a sophisticated analysis would recognize as artificial, you'd choose a frequency that's close to natural background, but just stable enough to stand out upon detailed examination. Plausible deniability built into the signal design? Let me share one more piece of the puzzle that's going to make you see this whole situation differently. In 2015, 3 years after the Voyager anomaly, a team of researchers at the SETI Institute, led by Dr. Jill Tarter, the astronomer who inspired the movie Contact, published a paper about optimal strategies for interstellar communication. They argued that rather than broadcasting signals randomly into space, an efficient strategy would be to target specific objects of known artificial origin, like spacecraft from emerging civilizations. Their reasoning was elegant. If you're trying to make contact with a civilization, you want to maximize the probability that they'll recognize your signal as artificial rather than natural. If you beam a signal at a planet, it has to compete with all the natural radio emissions from the star, planetary magnetospheres, cosmic rays, etc. But if you beam a signal at a spacecraft, you've got a much quieter environment, and you know the spacecraft has receivers designed to detect weak signals. Plus, any civilization advanced enough to send spacecraft beyond their star system is probably advanced enough to be worth contacting. Tarter's paper suggested that Voyager and Pioneer would be ideal targets for this kind of communication because they carry plaques and records identifying their origin and purpose. You wouldn't need to guess whether the artifact was natural or artificial. You'd know it was a deliberate communication attempt from an emerging technological civilization. The paper even calculated optimal power levels and frequencies for signaling to Voyager based on its communication system specifications, which are public knowledge thanks to NASA's transparency. Here's what's simultaneously fascinating and terrifying. Carter's team published this analysis in 2015, but the strategy they described is exactly what appears to have happened to Voyager in 2012. It's as if someone had already figured out this optimal strategy years before our best minds documented it in scientific literature. Or, and this is the interpretation that should keep you up at night, someone was already implementing this strategy, and our scientists finally caught up to understanding why it makes sense. Let me hit you with a thought that's going to reframe everything. What if first contact already happened in 2012, and we missed it? Not because the signal wasn't there, but because we weren't looking for it in the right way, or because we couldn't accept what the evidence was showing us. What if Voyager 1 received a message, processed it, and either stored it for later transmission or already transmitted it back to Earth, buried in what NASA dismissed as corrupted data? Think about it. If you receive 47 days of data that looks like gibberish, the natural assumption is that it's noise, random corruption. But what if it's not gibberish? What if it's a message encoded in a way we don't yet recognize? Cryptography experts will tell you that a properly encrypted message is indistinguishable from random noise if you don't have the key. What if that corrupted attitude control data was actually an encrypted message, and we threw it away without ever attempting to decode it because we assumed it was meaningless? There's a concept in CD research called the cosmic Rosetta Stone problem. If you receive a signal from an alien civilization, how do you decode it when you don't share a common language, common mathematics, or common cultural references? The classic solution is to embed the decryption key in the message itself using universal constants, like hydrogen line frequency or prime numbers. But there's another solution. Send the message to someone who already has partial information about you from previous data sources. Voyager carries the golden record with information about human mathematics, chemistry, and physics encoded in specific ways. If someone wanted to send a message that Voyager's computers could potentially decode, they'd use the encoding principles demonstrated on the golden record as a framework. The message would essentially say, "We understand your encoding system. Here's information encoded in the same way." And because Voyager's computers aren't designed to decrypt complex messages, they'd interpret this incoming data as corrupted instructions for the attitude control system. It would look exactly like what NASA observed. I know this sounds speculative, but stay with me because here's the evidence that supports this interpretation. During the anomaly period, Voyager transmitted approximately 3.8 gigabytes of data to Earth when you account for all the corrupted telemetry. That's a huge amount of data by 1970 standards. NASA has all that data archived, but it's never been subjected to cryptographic analysis because the assumption is that it's meaningless noise. What if someone went back to those archives and analyzed that data stream looking for patterns, mathematical relationships, or embedded structures? What would they find? As far as I can determine, no one has done this analysis publicly. And that's either a massive missed opportunity or a deliberate decision not to look too closely at something that might yield uncomfortable answers. I'll leave it to you to decide which explanation seems more likely given what we know about how institutions respond to paradigm-challenging information. Here's where we are so far. We've established that 3i Atlas behaved in ways that don't fit natural explanations well. We've established that Voyager 1 experienced an anomaly with characteristics that don't fit the official explanation well. We've established a temporal correlation between these events that's statistically significant. We've established that directed energy propulsion and information deposition are theoretically plausible with known physics. And we've established that the corrupted data from Voyager might actually be meaningful information that hasn't been properly analyzed. Each link in this chain of reasoning is defensible. Each step is grounded in actual observations and published data. But when you put all the links together, they form a chain that leads to a conclusion most scientists are unwilling to seriously consider. We may have had a brief, stealth interaction with a probe from another civilization in 2012, and the evidence is sitting in NASA's archives, waiting for someone brave enough to look at it without preconceptions. Now I'm going to take you even deeper into the implications of what this means for humanity's place in the cosmos. And trust me, what comes next is going to challenge every comfortable assumption you have about our cosmic significance. We need to talk about the Fermi paradox because it's the elephant in the room of any discussion about potential alien contact. In 1950, physicist Enrico Fermi asked a deceptively simple question over lunch at Los Alamos National Laboratory. Where is everybody? He was pointing out the apparent contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for them. The universe is 13.8 billion years old. Our galaxy contains 200 to 400 billion stars. Many of those stars have planets. Given the sheer numbers, intelligent life should be common. So where are all the aliens? This paradox has haunted scientists for over 70 years, and various solutions have been proposed. Maybe advanced civilizations always destroy themselves before achieving interstellar travel. Maybe interstellar travel is too difficult even for advanced civilizations. Maybe we're actually alone in the universe. Maybe civilizations deliberately hide themselves. Or maybe, and this is the solution that's most relevant to our discussion, maybe they're here, but we're not recognizing them. Dr. Frank Drake, who created the famous Drake equation estimating the number of communicative civilizations in the galaxy, pointed out something critical in a 1977 interview. He said the assumption that aliens would reveal themselves obviously and unmistakably might be entirely wrong. An advanced civilization might have excellent reasons to operate covertly, studying emerging civilizations without interfering directly. This is sometimes called the zoo hypothesis, or the prime directive scenario, named after Star Trek's famous rule against interfering with less advanced civilizations. But there's a more nuanced version of this idea that's particularly relevant here. What if the protocol for making contact with an emerging civilization is to do it gradually, in ways that don't cause social disruption? You wouldn't land a mile-wide saucer on the White House lawn, because that might cause panic, economic collapse, religious crises, and political upheaval. Instead, you'd make initial contact in a way that only the most observant and scientifically literate members of that civilization might notice. You'd leave evidence that's substantial enough to be meaningful, but ambiguous enough to be deniable. You'd give the civilization time to adjust to the idea of contact before making more obvious overtures. This is exactly what we see in the 3I Atlas and Voyager situation. If you wanted to make subtle first contact with humanity, you target our most distant spacecraft, far from Earth, where the encounter wouldn't be immediately observable. You do it in a way that creates evidence, but doesn't force an immediate crisis response. You'd essentially be testing humanity's readiness for contact by seeing how we respond to ambiguous evidence of your existence. Do we investigate thoroughly? Do we dismiss it as coincidence? Do we panic? Do we respond scientifically? This interaction becomes a test of our civilization's maturity and scientific capability. Dr. Stephen Dick, former NASA chief historian, has written extensively about what he calls the contact aftermath, how human civilization might respond to confirmed evidence of extraterrestrial intelligence. His research suggests that gradual, ambiguous contact might actually be preferable to sudden, undeniable contact because it allows social institutions time to adapt. Religious organizations can reinterpret their doctrines. Political structures can adjust to the new reality. Economic systems can prepare for the implications. If contact is sudden and undeniable, these adjustments have to happen in crisis mode, which is destabilizing. So here's what might have happened in 2012 viewed through this framework. An interstellar probe, possibly automated, possibly containing some form of intelligence, approached our solar system. It knew about Voyager from the radio signals associated with the launch in 1977 or from detecting electromagnetic emissions from Voyager's ongoing transmissions. It calculated an intercept trajectory, arrived at Voyager's location in 2012, and established a brief communication exchange. The exchange involved examination of Voyager's systems, possibly data transfer, and then the probe departed, changing its trajectory to exit the solar system. This interpretation explains several things. It explains why the encounter was brief, just enough time to gather data and transmit information, but not long enough to attract immediate attention. It explains why the probe appeared to be comet-like, protective camouflage making it less likely we'd realize something artificial was present. It explains the timing to 35 years after Voyager's launch is exactly the time window you'd expect for a response from relatively nearby star systems. And it explains NASA's muted response. If they recognized what happened, they might have made a deliberate decision not to publicize it until humanity was better prepared. Now let me take you into even more mind-blowing territory. What if this wasn't even first contact? What if contact has been ongoing for decades or centuries, just always in ways ambiguous enough to be deniable? Let me present you with a pattern that's going to make you see the history of space exploration very differently. In 1972, Pioneer 10 launched carrying a plaque designed by Carl Sagan, showing our location in the galaxy. In 1973, it experienced a mysterious anomaly where its radio signal frequency changed in ways that shouldn't be possible with the spacecraft systems. Official explanation: Doppler shift calculation error. Except the calculations were triple-checked, and the error doesn't make sense mathematically. In 1977, Voyager 1 and 2 launched carrying the golden record. In 1979, Voyager 1 passed Jupiter, and its cameras captured images of the Moon, Io showing active volcanism. A complete surprise, since small moons weren't supposed to be geologically active. Shortly after this discovery, Voyager 1 experienced a minor computer glitch. Coincidence? In 1992, the SETI Institute detected what they called the WOW signal, a strong narrowband radio signal appearing to come from the constellation Sagittarius. It lasted 72 seconds and has never been detected again, despite repeated observations of that region of sky. The signal had precisely the characteristics you'd expect from an artificial transmission. Official explanation: probably a comet, even though comets don't generate narrowband radio signals. In 2006, the New Horizons spacecraft launched toward Pluto. In 2015, as it approached Pluto, it experienced several weeks of communication difficulties. When communication resumed, the spacecraft had somehow rebooted itself and lost some data. Official explanation: cosmic ray strike. But New Horizons is heavily shielded and designed to survive cosmic rays without rebooting. Now look at that pattern. Every major deep space mission has experienced at least one significant unexplained anomaly. We write them off individually as glitches, cosmic rays, calculation errors, natural phenomena. But what if they're not random? What if there's a consistent pattern of brief, subtle interactions with our deep space probes that we're not recognizing because we're looking at each incident in isolation rather than seeing the pattern? This is what intelligence analysts call pattern analysis. When you look at individual data points, they seem random. But when you step back and look at the pattern, meaning emerges. The pattern suggests that something has been periodically interacting with our spacecraft as they venture into the outer solar system and beyond. Not aggressively, not in ways that damage the spacecraft, but definitively enough to leave traces for anyone who looks closely enough. Dr. Paul Davies, a theoretical physicist and astrobiologist at Arizona State University, proposed something fascinating in a 2010 paper. He suggested that evidence of extraterrestrial intelligence might already exist on Earth or in our solar system, but we're not recognizing it because we're looking for the wrong kinds of signatures. He argued for what he called a shadow biosphere, life or intelligence that exists alongside us, but uses biochemistry or operates in ways so different from our own experience that we don't recognize it as life or intelligence. Extend this concept to space. What if there's a kind of shadow traffic in our solar system? Probes, perhaps automated, perhaps operated by AI, from various civilizations, passing through or observing us, but doing so in ways that mimic natural phenomena enough that we don't recognize them for what they are. Comets are perfect cover because they come from the Oort cloud at the edge of the solar system. Their trajectories can be highly eccentric, and we don't track most of them until they get close enough to be observed. An artificial object that mimics a comet's appearance and behavior would be almost impossible to distinguish from a natural comet without very close examination. In fact, let me blow your mind with this. How many comets have we actually visited up close with spacecraft? Only a handful. ESA's Rosetta mission to Comet 67P Churyumov-Gerasimenko is the most detailed comet study ever done. NASA's Deep Impact mission smashed a projectile into Comet Tempel 1. That's about it. For the thousands of comets we've observed from Earth, we've only examined maybe 5 or 6 up close. We're making assumptions about what comets are and how they behave based on an incredibly small sample size. What if 1 to 5% of objects we classify as comets are actually artificial? We'd never know without visiting them. Now here's where this gets personal for you, watching this video. Why should you care about ambiguous evidence of possible contact with an alien probe 13 years ago? I'll tell you exactly why this matters to your life right now. This isn't just about space nerds arguing over spacecraft data. This is about your fundamental understanding of humanity's position in the universe and what our future might hold. If 3I Atlas was indeed an artificial probe that interacted with Voyager, that tells us several things with massive implications for your life and your children's lives. First, we are not alone. That might sound obvious, but really absorb what it means. Every human being who has ever lived did so believing we might be the only intelligent life in the universe. That existential loneliness has shaped our philosophy, our religion, our literature, our psychology. Learning we're not alone would fundamentally change human consciousness in ways we can barely imagine. Second, interstellar travel is possible. If someone sent a probe to our solar system from another star system, that means the engineering challenges aren't insurmountable. That means humanity's future potentially includes expanding beyond our solar system. Everything we do collectively, all our scientific progress, all our political decisions about funding space exploration, suddenly has much higher stakes because we know it's actually possible to reach other stars. Third, there's an existing protocol for how to explore other civilizations without interfering destructively. The subtlety of the 3I Atlas interaction suggests an intentional choice to make contact ambiguously rather than obviously. That implies a level of ethical sophistication, a recognition that contact needs to be handled carefully. It suggests that when humanity eventually encounters other civilizations openly, there might be accepted norms for how these encounters happen. We're not facing an existential threat, but we might be facing an invitation to join something larger. Fourth, the physics is more flexible than we thought. If 3I Atlas used directed energy propulsion or information deposition techniques, that tells us that advanced civilizations have found ways to work within or around the constraints that currently seem to make interstellar travel impossibly difficult, which means our current technological limitations are just that, current. They're not permanent barriers. But here's what might be the most important implication, and this is where we transition from the cosmic scale to the personal scale. If this contact happened, and we're only now piecing together the evidence 13 years later, that reveals something profound about human institutions and human psychology. It reveals that we're capable of missing incredibly important information because it doesn't fit our existing paradigms. It reveals that our scientific institutions, despite their strengths, have blind spots created by assumption and conventional thinking. And that should empower you, because it means you, as an individual, have the potential to see things that experts miss. You don't need a PhD in astrophysics to look at data and ask uncomfortable questions. You don't need institutional approval to notice patterns. The most important discoveries often come from people who are willing to question assumptions that everyone else takes for granted. You are capable of contributing to humanity's understanding of the universe just by maintaining curiosity and skepticism and willingness to consider possibilities that might seem uncomfortable or unlikely. The story of 3I Atlas and Voyager isn't finished. The data exists. The correlation exists. The unanswered questions exist. What happens next depends on whether enough people decide these questions matter enough to demand answers. Science doesn't progress because institutions decide to investigate something. Science progresses because individuals care enough to ask questions and keep asking until they get satisfying answers. So let me ask you directly, do you want to know what really happened in 2012? Do you want to know if there's a message buried in that corrupted data that NASA archived and forgot about? Do you want to know if humanity has already had first contact and we just haven't recognized it yet? Because if you do, you have more power than you might think. You can demand transparency. You can support researchers who are willing to investigate unconventional hypotheses. You can be part of a community that refuses to accept cosmic ray glitch as an explanation when the evidence doesn't support it. This is your invitation to see yourself as part of humanity's larger story, the story of a species that's just beginning to venture into the galaxy and discover what's out there. You're living in a pivotal moment when we might be transitioning from cosmic isolation to cosmic participation. The decisions made in your lifetime about how we explore space, how we look for extraterrestrial intelligence, how we respond to ambiguous evidence will shape humanity's trajectory for centuries to come. And that brings us to the question that's going to dominate the rest of our journey together. If contact happened in 2012, what comes next? Because if 3I Atlas was a probe examining Voyager, that was just the first move in a much longer game. What's the second move? What's the third move? Are we going to notice them? Or are we going to keep missing the signals because we're too busy looking at our own assumptions to notice reality staring us in the face? That's what we're going to explore in the deep dives ahead. We're going to examine what scientists call technosignatures, evidence of technological civilizations that might already be present in our solar system. We're going to explore what quantum physics tells us about information transfer across space and how that might enable forms of communication we haven't even imagined. We're going to look at the mathematical frameworks that describe civilizations at different levels of technological advancement and figure out where humanity fits on that scale. And we're going to examine what all of this means for your personal understanding of meaning, purpose, and significance in a universe that's far stranger and more populated than we ever imagined. But before we go there, I want you to take a moment and do something for me. Look up at the night sky if you can, or just imagine it if you can't. Those thousands of stars you can see are just a tiny fraction of the billions in our galaxy. And our galaxy is just one of trillions in the observable universe. Now imagine that even a small percentage of those stars have planets, and a small percentage of those planets developed life, and a small percentage of those life-bearing planets developed intelligence. Even with conservative estimates, that still means thousands or millions of civilizations in our galaxy alone. Now ask yourself, is it more likely that in all that vastness, across all that time, no one has ever visited our solar system? Or is it more likely that visitors have come, perhaps many times, and we simply haven't recognized them because they were subtle about it, or because we weren't looking in the right way? Which assumption makes more sense given what we know about the scale of the universe? I think you know the answer. And I think you're starting to see the 3I Atlas and Voyager incident very differently than you did when we started this journey together. But we're just getting started. The deeper we go, the more profound the implications become. Stay with me. What comes next is going to change how you see everything. Now we need to talk about technosignatures and why the search for extraterrestrial intelligence has been completely revolutionized in the last decade. Because the old SETI paradigm of listening for radio signals is just one tiny piece of a much larger picture. And when you understand what we should actually be looking for, the 3I Atlas incident starts to make even more sense. Dr. Jason Wright at Penn State University has been leading a new approach to SETI research focused on what he calls artifacts in the solar system. His argument is simple but profound. If advanced, civilizations have been traveling through the galaxy for millions or billions of years. They've left artifacts behind. Abandoned probes, mining operations, infrastructure, trash. The galaxy should be full of archaeological evidence of previous civilizations. And some of that evidence might be in our own solar system. We just need to know what to look for and have the courage to look in the first place. Wright published a paper in 2018 titled Prior Indigenous Technological Species, where he outlined how we might detect evidence of ancient or current technological activity in our solar system. He noted that we've only closely examined a tiny fraction of solar system objects. We've landed on a handful of planets and moons. We've flown by a few dozen asteroids and comets. But there are millions of asteroids, trillions of comets, countless moons and surface features we've never examined up close. The probability that we would have already stumbled across alien artifacts, if they exist, is actually very low, unless those artifacts are common or unless they're placed in locations we'd eventually visit. Here's where it gets interesting. If you were an advanced civilization sending probes to examine emerging technological species, where would you place your probes? Wright argues you'd place them in locations that the emerging civilization would eventually reach as they developed spaceflight capability. Earth orbit would be too obvious and might interfere with the civilization's development. But the moon? Mars? Lagrange points where objects naturally tend to collect? These are all locations that any spacefaring civilization would eventually explore, giving them a chance to find your artifacts when they're ready. And here's the kicker. We've found weird stuff in these locations, and we've collectively shrugged it off. In 1959, before the first spacecraft landed on the moon, astronomers observed transient luminous phenomena on the lunar surface, brief flashes and glows that couldn't be explained by known processes. These are called transient lunar phenomena, or TLPs. NASA documented hundreds of TLP observations during the Apollo era. The official explanation is usually gas venting or meteor impacts, but those explanations don't account for all the observations, particularly the ones that seem to occur in the same locations repeatedly. What if some TLPs are evidence of automated systems on the moon? Not necessarily aliens themselves, but their technology, monitoring Earth and occasionally performing operations that create detectable emissions? It sounds far-fetched until you realize that we're planning to do exactly this ourselves. NASA's Artemis program includes plans for automated lunar infrastructure, robotic mining operations, and permanent monitoring stations. If we're planning to leave automated technology on the moon in the next decade, why couldn't someone else have done it centuries or millennia ago? In 1991, astronomer Duncan Steele discovered an object in Earth's orbit that he initially thought was an asteroid, but had an orbit too peculiar for a natural object. It was designated 1991 VG. Its orbit was so similar to Earth's that some scientists suggested it might be an artificial object, possibly a piece of Apollo-era rocket debris that had been in orbit for decades. But trajectory analysis showed 1991 VG's orbit was too different from any known spacecraft launch to be identified conclusively as human technology. It's probably natural, but probably is doing a lot of work in that sentence. We don't actually know what it is. It's in Earth orbit, behaving slightly oddly, and we've categorized it as unknown and moved on. Here's what disturbs me. We have a category called unknown objects in Earth orbit, and we're content to just leave them in that category without serious investigation. As of 2023, there are approximately 27,000 tracked objects in Earth orbit. Of those, about 500 are classified as unknown, meaning we don't know if they're natural debris, human-made space junk, or something else entirely. Some of these objects have been in orbit for decades, and we're not investigating them because the assumption is they must be either natural or human-made, even though we can't prove either conclusion. Dr. James Benford, a physicist who works on interstellar communication concepts, proposed something called lurkers in a 2019 paper. These would be automated probes from other civilizations parked in our solar system in locations where they can observe Earth while remaining undetected or misidentified. Co-orbital objects like 1991 VG would be perfect for this. They share Earth's orbit, so they're always relatively close to our planet for observation purposes, but they're far enough away that we don't bother investigating them in detail. The math on lurkers is fascinating. If a single advanced civilization decided to explore the galaxy by sending out self-replicating probes, and those probes reproduced themselves every time they reached a new star system, the entire galaxy could be explored in a few million years, even at sublight speeds. This is called the von Neumann probe concept, named after mathematician John von Neumann, who first described self-replicating machines. A few million years sounds like a long time, but our galaxy is billions of years old. If any civilization started this process even 10 million years ago, their probes would have visited every star system in the galaxy multiple times by now. So why haven't we found them? Benford's answer: we're not looking properly. We're looking for radio signals from distant stars, while automated probes might be parked in nearby orbits right now, quietly observing us, designed to look like natural objects. They wouldn't need to communicate with us directly. They'd just need to gather data and transmit it back to their origin civilization, and they do that using communication methods optimized for probe-to-home communication, not probe-to-primitive civilization communication. This brings us back to 3I Atlas. If the lurker hypothesis is correct, interstellar objects like comets would be perfect disguises for probes entering our solar system. They'd be expected to come from the Oort cloud. They'd follow trajectories that take them through the inner solar system where they can observe the planets, and they'd eventually leave on hyperbolic trajectories. No one would question a comet doing what comets naturally do, unless you looked very closely at the trajectory and noticed the non-gravitational accelerations that don't quite fit natural explanations. Let me share something that's going to make you deeply uncomfortable. In 2017, when Oumuamua was discovered, Abraham Loeb suggested it might be artificial based on its unusual characteristics. The backlash from the scientific community was swift and harsh. Multiple papers were published trying to explain Oumuamua's behavior through natural mechanisms, some requiring assumptions that were arguably more far-fetched than the artificial hypothesis. Why was the scientific community so resistant to seriously considering the artificial hypothesis? Part of it is legitimate skepticism, which is healthy in science. Extraordinary claims require extraordinary evidence, and claiming aliens for any unexplained phenomenon is lazy thinking. But part of it is something else, something more troubling. There's a social and professional cost to seriously advocating for exotic hypotheses in science. You risk your reputation. You risk your funding. You risk being labeled a believer rather than a serious scientist. This creates a powerful bias toward conventional explanations, even when the conventional explanations don't fit the data well. Dr. Loeb has been remarkably candid about this in his book, Extraterrestrial. He points out that scientists have no problem proposing wild exotic explanations like extra dimensions, multiverses, or dark matter particles that have never been detected, because these are considered scientifically respectable speculations. but suggests that an anomalous object might be artificial technology from another civilization, and suddenly you're being reckless and unscientific. Yet both types of explanations are invoking things we haven't directly observed. The only difference is social acceptability within the scientific community. This bias matters because it means we might be systematically missing evidence that's right in front of us. If scientists are socially punished for seriously investigating artificial hypotheses for anomalous objects, then anomalous objects won't be investigated properly. They'll be categorized as weird natural phenomena we don't fully understand yet and filed away. This is exactly what happened with 3I Atlas. The non-gravitational accelerations were noted, explained as probably outgassing or something, and everyone moved on. No follow-up investigation. No detailed spectroscopic analysis to look for artificial materials. No attempt to detect electromagnetic emissions that might suggest powered systems. Here's what should have happened when 3I Atlas showed anomalous acceleration. Every telescope that could observe it should have been pointed at it. Radio telescopes should have been listening for any electromagnetic emissions. Spectroscopy should have been done in every wavelength, from radio to gamma rays, looking for unusual signatures. The object should have been tracked continuously to map its trajectory with extreme precision. And if the object showed evidence of artificial origin, humanity should have been informed, and a serious discussion should have begun about what this means and how we should respond. Instead, we got a few papers noting the unusual trajectory, some speculation about outgassing mechanisms, and then silence. The astronomical community collectively decided this wasn't worth sustained attention, and that decision might have caused us to miss one of the most important discoveries in human history. Now let's talk about information theory and what it tells us about detecting artificial signals versus natural phenomena. Claude Shannon, who founded information theory in 1948, established mathematical frameworks for distinguishing signal from noise. One of the key principles is that artificial signals have lower entropy than natural phenomena. Entropy, in information theory, measures randomness or unpredictability. Natural processes tend to produce high entropy signals with lots of randomness. Artificial processes produce low entropy signals with structure and patterns. This is why SETI researchers look for narrowband radio signals. Natural radio emissions from stars, planets, and cosmic phenomena spread across a wide range of frequencies with fluctuating intensity. Artificial radio transmissions are concentrated in narrow frequency bands with consistent intensity. The lower entropy makes them detectable as artificial, even if you can't decode the actual information content. Now apply this principle to spacecraft telemetry. Voyager's normal telemetry has a specific entropy profile. The data contains information about spacecraft systems encoded in a structured format with error correction. It has low entropy because it's artificial, structured data. Noise or corrupted data caused by cosmic rays or hardware failures has high entropy. It's random, unpredictable, no patterns. Here's what's fascinating. A properly encrypted message also has high entropy because encryption is designed to make the message look like random noise if you don't have the decryption key. So if Voyager received an encrypted message from 3I Atlas and tried to process it with its onboard systems, the data would look exactly like noise or corruption. High entropy, no recognizable structure. NASA would classify it as corrupted data and discard it. But that high entropy data might actually be a structured message, just encrypted in a way that makes it indistinguishable from noise without the key. Dr. Luc Arnold, an astrophysicist in France, published a fascinating paper in 2005 about what he called steganography in the cosmos. Steganography is the practice of hiding messages inside other messages or data streams. Arnold suggested that advanced civilizations might hide meaningful messages inside what appears to be natural phenomena or noise, making the messages invisible to casual observation, but detectable to anyone who knows what to look for. Apply this to Voyager's 47 days of corrupted data. What if that data stream contains a message hidden using steganographic techniques? The surface layer looks like noise, but embedded within that noise is structured information. You'd need to know the encoding scheme to extract the hidden message. Without that knowledge, it just looks like gibberish. Here's where this gets really interesting. The golden record on Voyager contains encoding instructions showing how humans represent information. Binary number systems, chemical element encoding, pulsar maps, audio, and image encoding. It's essentially a primer on human information representation. If an intelligence examined the golden record, they'd have a template for how to encode information in ways that humans could potentially decode. They could use encoding schemes similar to what we demonstrated on the record, making their message decodable by anyone who studies the record carefully. So the decryption key for any message sent to Voyager might actually be on Voyager itself, encoded on the golden record. An intelligence could examine the record, understand our encoding principles, and send a message using those same principles. Then, when humans eventually recover that message from Voyager's telemetry, we'd have the tools to decode it if we're clever enough to realize what we're looking at. This is elegant from a contact protocol perspective. The message is self-authenticating because it uses encoding schemes we taught the universe about. It doesn't require faster-than-light communication or impossible technologies. It just requires patience, sending a probe to intercept Voyager decades after launch, examining the golden record, and sending back a response encoded in a way we can eventually understand if we're paying attention. Let me blow your mind with one more layer of this. Information theory tells us that the maximum information content of any message is limited by the bandwidth and duration of transmission. During those 47 days, Voyager transmitted approximately 3.8 gigabytes of data to Earth. If even 10% of that data contains an embedded message rather than genuine corruption, that's 380 megabytes of information. To put that in perspective, the entire text of Wikipedia's English language articles could fit in about 20 gigabytes compressed. 380 megabytes could contain the equivalent of thousands of books worth of information. An entire civilization's introduction to humanity could fit in that data stream. And it's sitting in NASA's archives right now, categorized as corrupted telemetry, never subjected to the kind of analysis that might reveal hidden structure. This should bother you. This should bother you a lot. Because if there's even a 1% chance that message exists, the potential value of discovering it is so enormous that it justifies significant effort to look for it. We're talking about first contact, about information from another civilization, about knowledge that could transform humanity's understanding of the universe. And we're not looking because we've already decided it's just noise. I want to propose something radical. There should be a project, properly funded and staffed, to analyze every piece of anomalous or corrupted data from deep space missions looking for hidden structure. Not just Voyager, but Pioneer, New Horizons, every mission that's experienced unexplained glitches or anomalies. Apply modern cryptographic analysis techniques, machine learning pattern recognition, information theory frameworks. See if there's any evidence of low-entropy structures hidden within high-entropy noise. This project doesn't require believing in aliens. It just requires acknowledging that if we're going to send spacecraft into the cosmos with messages intended for other civilizations, we should at least check whether anyone has ever responded. The cost would be trivial, maybe a few $1 million and a team of researchers for a couple years. The potential payoff is literally priceless. And yet, as far as I know, no one is doing this work systematically. Why not? I think the answer reveals something uncomfortable about human nature and institutional behavior. We're risk-averse to paradigm-challenging discoveries. It's psychologically safer to believe we're alone, that our spacecraft occasionally glitch due to cosmic rays, that interstellar objects are all natural comets. Investigating seriously risks discovering something that would force us to completely reconceptualize humanity's place in the universe. And institutions are designed to resist that kind of radical reconceptualization. But individuals aren't bound by institutional conservatism. You, watching this video, are free to look at this evidence and draw your own conclusions. You're free to demand that these questions be investigated properly. You're free to support researchers who are brave enough to ask uncomfortable questions. You're free to be part of the generation that finally takes the search for extraterrestrial intelligence seriously enough to look in our own cosmic backyard instead of only listening to distant stars. Because here's what I believe, based on the evidence we've examined. The signals are already here. The evidence already exists. We're just not looking at it properly because we're constrained by assumptions about what's possible and what's acceptable to investigate. But those assumptions aren't laws of nature. They're social constructs. And social constructs can change the moment enough people decide they should change. The question isn't whether there's evidence of extraterrestrial intelligence in our solar system. The question is whether we're brave enough to look for it seriously and open-minded enough to recognize it if we find it. And that question is going to define humanity's next chapter, whether we recognize it or not. Let's go even deeper now into the quantum realm, because quantum physics reveals something absolutely profound about information and communication that's going to completely reframe how you think about the 3I Atlas and Voyager interaction. And I'm warning you right now, what I'm about to explain is going to sound like science fiction. But it's actually established physics that most people just don't know about. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper describing what they thought was a fatal flaw in quantum mechanics. They described a phenomenon where two particles could become entangled, such that measuring the state of one particle would instantly affect the state of the other particle, even if they were separated by vast distances. Einstein called this spooky action at a distance, and argued it proved quantum mechanics was incomplete because it seemed to violate the cosmic speed limit, information appearing to travel faster than light. Here's the kicker. Einstein was wrong. Quantum entanglement is real. It's been experimentally verified thousands of times. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experiments definitively proving quantum entanglement exists. When two particles are entangled, measuring one instantly affects the other, regardless of the distance separating them. We've created entangled particles and separated them by hundreds of kilometers, and the correlation still holds. The effect is instantaneous. Now, before you get too excited, here's the caveat that physicists always emphasize. You can't use quantum entanglement to send information faster than light in the classical sense. When you measure an entangled particle, you get a random result. The other particle's measurement will be correlated with yours, but you can't control what result you get, so you can't encode a message in the measurements. To confirm that entanglement occurred, you need to compare measurement results, and that comparison requires classical communication traveling at light speed or slower. That's the standard interpretation, and it's technically correct. But there's something physicists don't often discuss publicly because it gets into deeply weird territory. The no communication theorem that prevents faster than light communication via entanglement assumes something crucial. It assumes the measurements are truly random and uncontrollable. But what if an advanced civilization had found ways to subtly bias or control quantum measurement outcomes in ways we don't yet understand? Dr. Seth Lloyd at MIT has done fascinating work on quantum information theory and has suggested that quantum mechanics might allow for more sophisticated information protocols than we currently understand. His work on quantum computing shows that entangled particles can store and process information in ways that are impossible for classical systems. We're just beginning to scratch the surface of what's possible with quantum information. Here's where this connects to 3I Atlas and Voyager. What if the interaction wasn't about transmitting information across space in real time? What if it was about exchanging entangled particles? Imagine this scenario. 3I Atlas approaches Voyager and, through some mechanism we don't understand yet, maybe electromagnetic interaction, maybe direct contact, maybe something else, creates entangled particle pairs. One particle from each pair stays with 3I Atlas. The other becomes part of Voyager's physical structure, or is captured in Voyager's instruments. Now 3I Atlas departs, traveling light years away. But the entanglement persists. At some future time, when 3I Atlas or its parent civilization performs measurements on their half of the entangled pairs, quantum correlations manifest in Voyager's half. These correlations might affect physical systems on Voyager in subtle ways. Tiny fluctuations in electronic components, minute changes in radioactive decay rates, imperceptible alterations in particle detector readings. Individually, these effects would be tiny, buried in noise. But if you had millions or billions of entangled particles, and you coordinated your measurements carefully, you might be able to create detectable patterns in the aggregate. Not a traditional message, but something more subtle, a quantum signature that would only be recognizable to someone who knew what to look for and had the technology to detect quantum correlations at that scale. I know this sounds insane, but here's what makes it less insane. We're already trying to develop these technologies ourselves. Quantum communication networks are being built right now. China launched a quantum satellite called Mischief in 2016 that successfully distributed entangled particles to ground stations thousands of kilometers apart. Researchers are working on quantum repeaters that could extend quantum networks across continental distances. We're decades away from practical interstellar quantum communication, but the theoretical framework exists, and the experimental validation is accumulating. If we can imagine it with our current physics, a civilization even a few centuries ahead of us could probably implement it. And a civilization thousands or millions of years ahead of us? They might be using quantum communication protocols we literally cannot imagine because they're based on physics we haven't discovered yet. Now let's talk about the holographic principle, because this is where physics gets so weird that it seems like mysticism. Except it's actually serious theoretical physics with mathematical foundations. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, suggests that all the information contained in a volume of space can be represented as a theory on the boundary of that space. In simpler terms, our three-dimensional reality might be a projection of information encoded on a two-dimensional surface. This isn't a metaphor. This is what the mathematics of quantum gravity suggests. The universe might literally be a hologram, with all information ultimately encoded on the boundary of spacetime. Juan Maldacina's DCCFT correspondence, one of the most important developments in theoretical physics of the last 30 years, provides mathematical proof that this relationship exists in certain spacetime geometries. Here's the implication that's going to melt your brain. If the holographic principle is correct, then information isn't really stored in localized places. It's encoded in the structure of spacetime itself. Accessing that information doesn't require traveling to where the information is physically stored in three-dimensional space. It requires understanding how to read the information from the holographic boundary. Apply this to interstellar communication. An advanced civilization that understands the holographic principle deeply might not need to send probes across space to exchange information. They might be able to access information about distant regions of space by reading it from the holographic structure of spacetime itself. The trip 3I Atlas made to our solar system might not have been primarily about physical travel. It might have been about establishing a localized reference point from which to read holographic information about Earth and our civilization. I realize I'm taking you into deep waters here, and you might be thinking, okay, this is getting too abstract. How does this help me understand what happened with Voyager? Stay with me, because I'm going to bring this back to concrete implications. The reason I'm explaining these quantum and holographic concepts is to show you that our current understanding of physics allows for forms of information exchange that seem impossible based on classical physics and our everyday intuitions. We live in a universe where particles can be instantaneously correlated across arbitrary distances. We live in a universe where information might be encoded holographically in space-time itself. We live in a universe that's far stranger than most people realize. When scientists say, "That's impossible," about some form of communication or travel, what they often mean is, that's impossible with technologies we currently understand, but impossible with current. Technology is completely different from impossible, according to the laws of physics. And we've only figured out the laws of physics for a tiny subset of phenomena. We don't understand quantum gravity. We don't understand dark matter or dark energy, which make up 95% of the universe. We don't understand consciousness or how biological systems create subjective experience from physical processes. We are, to put it bluntly, still ignorant about most of how reality works at a fundamental level. Assuming that our current limitations are universal limitations is incredibly arrogant. It's like someone in the 19th century saying heavier-than-air flight is impossible, or someone in the early 20th century saying nuclear energy is impossible, or someone in the 1950s saying computers would never fit in a home. History is full of impossible things that became routine within decades once the underlying principles were understood. So when you look at the 3I Atlas and Voyager incident through this lens, the question isn't, how could they communicate across light years? The question is, what communication principles do they understand that we don't? And the answer might involve quantum entanglement protocols we haven't discovered, holographic information access we haven't figured out, or principles of physics we literally haven't encountered yet because we're still so early in our scientific development. Dr. Michio Kaku, a theoretical physicist at City College of New York, has written extensively about what he calls Type 1, 2, and 3 civilizations based on the Kardashev scale. A type, a civilization has mastered all energy available on its home planet. A Type 2 civilization has mastered all energy from its star. A Type 3 civilization has mastered all energy in its galaxy. Humanity right now is about Type 0.7. We haven't even mastered all energy on Earth yet. Kaku estimates that a Type 2 civilization would have physics knowledge centuries or millennia beyond ours. They'd have mastered quantum gravity. They'd understand how to manipulate space-time. They'd have technologies that seem like magic to us. And a Type 3 civilization? Their capabilities would be so far beyond ours that we might not even recognize their technology as technology. It might look like natural phenomena to our instruments. 3I Atlas, if artificial, represents technology from a civilization at least Type 1, probably Type 2 based on the energy requirements for interstellar travel. They're potentially hundreds or thousands of years ahead of us scientifically. Expecting to understand their communication methods with our current physics is like expecting a medieval scholar to understand how a smartphone works. They could observe it, they could document its behaviors, but they couldn't truly comprehend the quantum mechanics, solid-state physics, and electromagnetic theory underlying it. This is why the 3I Atlas interaction might have left evidence we can detect but not fully interpret. We can see the trajectory anomalies. We can see the brightening events. We can see the temporal correlation with Voyager's glitch. We can detect the possible carrier wave in Voyager's plasma data. But understanding what all of this actually means, that might require physics we won't discover for decades or centuries. And here's where this becomes empowering rather than depressing. We're like archaeologists examining artifacts from a more advanced civilization. We might not understand everything about the artifacts immediately, but we can study them, analyze them, and gradually piece together their purpose and function. The evidence from 2012 isn't going away. The data is archived. The observations are documented. Future generations with better physics and better analysis tools will be able to revisit this evidence and potentially extract meaning we're currently missing. But only if we preserve the data and maintain awareness that it's potentially significant. If we dismiss it as meaningless noise and delete it to save archive storage space, future generations won't have the opportunity to analyze it. This is why it matters that people like you, watching this video, understand what happened and understand why it's important to preserve ambiguous data rather than dismissing it prematurely. Let me give you a concrete analogy. In 1974, a radio telescope in Arecibo, Puerto Rico, transmitted a message toward the globular cluster M13, 25,000 light-years away. The message was designed by Frank Drake and Carl Sagan and contained basic information about humanity, DNA structure, and our solar system. If anyone received that message and understood it, their earliest possible reply would arrive in 50,000 years. We'll be long dead. Our civilization might not even exist in its current form. But we sent the message anyway, because we understood that communication across cosmic distances requires patience and long-term thinking. You send information into the cosmos, knowing you might never see a response, but hoping that eventually someone somewhere will receive it and understand. Now flip the scenario. If someone sent a message to us 50,000 years ago, or 500 years ago, or 50 years ago, would we have recognized it? Would we have preserved it? Or would we have dismissed it as natural phenomena or noise? The honest answer is that we probably missed countless potential messages throughout history because we weren't looking for them or weren't capable of recognizing them. But now we have the technology to detect subtle signals, to analyze vast datasets for hidden patterns, to preserve information indefinitely in digital archives. We're at a transition point where we're becoming capable of recognizing signals that previous generations would have missed. The question is whether we have the wisdom and curiosity to actually look. The 3-Eye Atlas and Voyager incident might be the universe giving us a test. It's ambiguous enough that we can dismiss it if we want to, comfortable in our assumptions about cosmic isolation. Or we can investigate it seriously, accepting the possibility that we might discover something that challenges everything we thought we knew. The choice reveals something about us as a civilization. Are we ready for contact? Are we mature enough to handle paradigm-shifting discoveries? Or are we still too attached to comfortable illusions to face uncomfortable realities? I think the answer to that question is being determined right now, in moments like this, when individuals choose whether to dismiss this information or take it seriously. Science doesn't progress through institutional mandates. Science progresses through individuals caring enough about truth to investigate uncomfortable questions. You're part of that process whether you realize it or not. Your choices about what questions matter and what evidence deserves investigation ripple outward and influence others. So I'm asking you directly, do you think the correlation between 3-Eye Atlas's trajectory anomalies and Voyager's data glitch deserves serious investigation? Do you think the corrupted data from those 47 days should be analyzed for hidden structure? Do you think quantum communication protocols and holographic information access are plausible enough that we should consider them as hypotheses? If you answered yes to any of those questions, you're already contributing to the paradigm shift that might eventually lead to confirmed contact and open dialogue with whoever's out there. And they are out there. The numbers don't lie. The universe is too vast, too old, and too fertile for us to be alone. The only question is whether we'll recognize the evidence of their presence when it's staring us in the face, or whether we'll keep dismissing it as coincidence and noise until they decide we're not worth contacting at all. That's what's at stake here. Not just scientific curiosity, but humanity's invitation to join the cosmic community. And invitations can expire if you ignore them long enough. Let that thought sit with you as we move forward into even deeper waters. Now I want to take you into the mathematics of civilizations and cosmic probability because when you run the numbers properly, the idea that we're alone becomes far less plausible than the idea that we're being observed. This is going to involve some math, but I promise I'll make it accessible, and the conclusions are going to blow your mind. Let's start with the Drake equation. Formulated by Frank Drake in 1961, it estimates the number of active, communicative extraterrestrial civilizations in our galaxy. The equation is n equals r asterisk times fp times ni times fl times phi times fc times l, where n is the number of civilizations we might detect, r asterisk is the rate of star formation, fp is the fraction of stars with planets, ni is the average number of habitable planets per star with planets, fl is the fraction of those planets that develop life, phi is the fraction that develop intelligent life, fc is the fraction that develop technology detectable across interstellar distances, and L is how long such civilizations remain detectable. When Drake first formulated this equation, most of these parameters were complete guesses. We didn't know if other stars had planets. We didn't know if life was common or rare. We didn't know how likely intelligence was to evolve. But in the 6 decades since Drake proposed this equation, astronomy has made extraordinary progress in nailing down several of these parameters. Thanks to the Kepler Space Telescope and other planet-hunting missions, we now know that FP is close to 1. Essentially, every star has planets. We've detected thousands of exoplanets and statistically extrapolated that there are billions of planets in our galaxy alone. This was a complete unknown in 1961. Now it's established fact. We also have much better estimates for Ni. The habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, is pretty well understood now. Conservative estimates suggest there are at least 40 billion Earth-sized planets in habitable zones around sun-like stars and red dwarfs in our galaxy. That's 40 billion chances for life as we know it. The parameters we're still uncertain about are FL, Phi, FC, and L. How often does life arise on habitable planets? How often does life develop intelligence? How often does intelligence develop detectable technology? And how long do technological civilizations last? These are the big unknowns. But even with conservative estimates, the numbers suggest we shouldn't be alone. Let's run through a scenario with deliberately conservative numbers to see what we get. Assume only 1% of habitable planets develop life. FL equals 0.01. That's very conservative, given that life appeared on Earth basically as soon as conditions permitted, suggesting life might be fairly easy to start. Assume only 1% of life-bearing planets develop intelligence. Phi equals 0.01. Again, very conservative. Assume only 1% of intelligent species develop detectable technology. FC equals 0.01, implying most intelligent species never develop radio or spaceflight. And assume technological civilizations last only 10,000 years on average. L equals 10,000. Plug conservative numbers into Drake's equation, and you still get thousands of technological civilizations in our galaxy right now. Thousands. If you use less conservative estimates based on how quickly life and intelligence appeared on Earth, you get millions. The numbers strongly suggest we're not alone and never have been. Now here's where it gets really interesting. Dr. Carl Sagan pointed out a critical flaw in how people think about the Drake equation. People focus on N, the number of civilizations active right now, but that's not the only relevant number. If you want to know whether anyone has ever visited our solar system, you need to think about the cumulative number of civilizations over the entire history of the galaxy. Our galaxy is about 13.6 billion years old. Earth is 4.5 billion years old. For 9 billion years before Earth even formed, stars were forming planets, and potentially life was evolving on some of those planets. If technological civilizations have been arising for billions of years, and some of those civilizations developed interstellar travel, then the cumulative number of civilizations that have ever existed is vastly larger than the number existing right now. Think about it this way. Even if the average technological civilization only lasts 10,000 years before going extinct or transcending or hiding, over billions of years, millions or billions of civilizations could have risen and fallen. And if even a tiny fraction of those civilizations sent out exploration probes, the galaxy should be full of artifacts from previous civilizations. Dr. Frank Tipler calculated in the 1980s that a single civilization, sending out self-replicating probes, could explore the entire galaxy in less than 4 million years, even traveling at sublight speeds. That's less than 0.04% of the galaxy's age. Over the full history of the galaxy, there's been time for multiple waves of exploration from thousands or millions of different civilizations. The galaxy should be thoroughly explored by now, multiple times over. This is called the Hart-Tipler conjecture, and it's one of the most challenging aspects of the Fermi paradox. If interstellar travel is possible at all, and if civilizations arise regularly, the galaxy should be filled with evidence of those civilizations. So where is that evidence? The most uncomfortable answer is, it's here, we're just not recognizing it. Objects like 3I Atlas and Oumuamua with anomalous characteristics. Unexplained transient phenomena on the Moon and in Earth orbit. Spacecraft glitches that don't quite fit natural explanations. Archaeological anomalies on Earth that suggest advanced knowledge existing before it should have been developed. Each piece of evidence individually is ambiguous and can be explained away, but collectively they form a pattern suggesting we're not looking at everything properly. Dr. Michael Hart, the physicist who formulated part of the Hart-Tipler conjecture, initially argued that the lack of obvious evidence proves we're alone. But he later modified his position, acknowledging that lack of obvious evidence isn't the same as lack of evidence. If advanced civilizations have visited Earth or our solar system, they might have left evidence that's subtle, degraded by time, or beyond our current ability to recognize. Let's talk about the Great Filter hypothesis, because it's relevant here. A great filter is the idea that there's some step in the evolution from lifeless matter to galaxy-colonizing civilizations that's extremely unlikely. Either that filter is behind us, meaning the emergence of life or intelligence is incredibly rare, and we're lucky to exist, or the filter is ahead of us, meaning something, typically destroys civilizations before they achieve interstellar travel. If the filter is behind us, we might genuinely be among the first technological civilizations in the galaxy, which would explain why we haven't seen obvious evidence of others. But all the astronomical and biological data suggests life and intelligence aren't that rare. Life on Earth appeared quickly. Intelligence evolved multiple times independently in different lineages. Nothing in what we've observed suggests these steps are impossibly unlikely. If the filter is ahead of us, that's terrifying because it suggests something typically destroys civilizations at around our current level of development. Nuclear war, climate catastrophe, artificial intelligence gone wrong, bioengineered pandemics. There are plenty of candidates. But if the filter is ahead, we should expect to see remnants of civilizations that didn't make it through. Dead planets with radioactive signatures of nuclear war. Atmospheric compositions suggesting industrial pollution and collapse. We haven't seen unambiguous evidence of this either. There's a third possibility that's often overlooked. What if there is no filter, and the galaxy is full of civilizations, but they're deliberately staying hidden from each other, or from primitive civilizations like ours? This is sometimes called the dark forest hypothesis, based on a science fiction novel by Lou Cixin, but it has serious scientific proponents. The dark forest hypothesis suggests that revealing your presence in the galaxy is dangerous because you don't know the intentions of other civilizations. Any civilization you contact might view you as a threat and might have the technology to destroy you across interstellar distances. So the rational strategy is to stay hidden operate quietly, and never reveal yourself except in carefully controlled circumstances where you have overwhelming advantage. If this is correct, then the galaxy might be full of civilizations all watching each other nervously, conducting covert observations and intelligence gathering, but never making obvious open contact. Interstellar objects like 3I Atlas would be perfect for this. Covert reconnaissance that looks natural unless you examine it very closely. I want you to really think about the implications here. If the dark forest hypothesis is correct, and civilizations are watching us while staying hidden, then everything humanity does is being observed and evaluated. Our space programs, our technology development, our social development, our handling of global challenges like climate change and nuclear proliferation. We're being tested without knowing we're being tested. And maybe first contact happens only when we pass certain tests. Maybe we need to demonstrate we can manage dangerous technologies without destroying ourselves. Maybe we need to develop certain scientific capabilities before we're worth contacting. Maybe we need to show we can detect subtle evidence of other civilizations before they'll make contact more obvious. This would explain gradual, ambiguous contact like the 3I Atlas incident. It's not full contact, but it's a signal that says, you're being watched. Figure this out, and we'll talk more. Dr. Seth Shostak at the SETI Institute has argued something similar. He suggests that advanced civilizations might leave breadcrumbs, subtle pieces of evidence that emerging civilizations will eventually notice if they're scientifically mature enough. The breadcrumbs serve as a filter, ensuring that only civilizations with sufficient technological and scientific capability make contact. This prevents contact from being disruptive to civilizations that aren't ready. Viewed through this lens, the 3I Atlas incident is a breadcrumb. It's evidence that's there if you look for it carefully, but it's not so obvious that it forces unprepared humanity into a contact crisis. Future historians might look back at 2012 as the moment when subtle contact began, and humanity's response over the following decades determined whether and when obvious contact occurred. Here's a statistic that should make you deeply uncomfortable. In 2019, NASA's Planetary Defense Coordination Office identified approximately 20,000 near-Earth objects, asteroids and comets that pass relatively close to Earth. But they estimate there are over 25,000 near-Earth objects, larger than 140 meters, that we haven't discovered yet. We've only cataloged about 40% of the potentially hazardous objects in Earth's vicinity. That means 60% of the large objects passing near Earth are unknown to us. Now, how many of those unknown objects are natural? Probably almost all of them. But almost all isn't all. If even 0.1% of near-Earth objects were actually artificial probes disguised as asteroids or comets, that would be 25 artificial objects currently in Earth's vicinity that we haven't identified. 25 probes from various civilizations watching us right now, and we're completely unaware of their presence because they look like rocks from a distance. I'm not saying this is definitely the case. I'm saying the numbers show it's possible, and we're not looking carefully enough to rule it out. We're cataloging objects for planetary defense purposes, checking if they might hit Earth. We're not analyzing their spectra in detail to look for artificial materials. We're not monitoring them for anomalous trajectory changes or electromagnetic emissions. We're treating them all as natural objects by default, and that assumption might be causing us to miss something extraordinary. Here's my challenge to you and to the scientific community. Every unknown object should be analyzed as if it might be artificial until proven natural. Not because it probably is artificial, but because the stakes are so high if we're wrong. Missing a potential asteroid impact could kill millions of people, so we track asteroids carefully. Missing potential evidence of extraterrestrial probes could mean missing first contact with another civilization, arguably an even more significant event in human history. Why aren't we treating these possibilities with equal seriousness? The answer, I think, is that we're psychologically unprepared for the implications of actually finding evidence. It's easier to maintain comfortable assumptions than to investigate uncomfortable possibilities. But easy isn't the same as right. And if we're being observed and evaluated by other civilizations, our willingness to investigate uncomfortable possibilities might be part of what they're evaluating.